I want you to picture yourself walking into a modern high-tech hospital. Or, maybe it's one of those futuristic medical diagnostic labs.
Right, the kind that feel almost like a sci-fi movie.
Exactly, like
Yeah.
stepping onto a spaceship. And what do you actually see when you walk through those doors? You probably notice the glowing screens first.
Oh, definitely.
Then you see the complex imaging systems humming in the corners, the perfectly sterile environments, those sleek touchpads mounted on the
It is
walls.
very visual.
It is. But while you're looking at all those flashing lights and marveling at the sophisticated software, you are almost certainly missing the invisible underlying skeleton that makes, well, every single piece of that technology possible.
Yeah, and that's by design, really. The most critical infrastructure in a medical setting is specifically designed to be ignored.
Which is crazy to think about.
It is, but we are naturally drawn to the digital brains of medical technology. The AI diagnostics, the high-resolution displays. But the physical bones of the machinery, they dictate whether those digital brains can actually function in the real world.
Okay, let's unpack this because I am intensely curious about how something as seemingly mundane as metal extrusions or raw aluminium profiles can actually be a critical driver of medical innovation.
It really is the foundation of it all.
Right. So today, for this deep dive, we are exploring the manufacturing reality behind modern healthcare. We're pulling back the curtain on some really fascinating insights from Eleanor Industries.
Yeah, the premier aluminium extrusion supplier based out of Gujarat, India.
Exactly. And by looking at how they custom engineer these structural profiles, we're going to see why you should care deeply about the literal nuts and bolts holding life-saving medical technology together.
What's fascinating here is that in the context of healthcare, material selection is never just a budget line item or a simple manufacturing preference.
It's much bigger than that.
It's a structural decision with life or death consequences. I mean, the physical framework of a medical device governs its safety, its mobility, and its clinical accuracy.
Wow.
Yeah, if that skeleton fails, the software running inside it is entirely useless.
So when we talk about that skeleton, we really have to deal with the immediate physical reality of a hospital environment first, right? Which is sheer mass.
Absolutely. The weight of these things is staggering.
The equipment, we're talking about battery banks for critical care monitors, the internal components of an MRI, portable X-ray machines. These things are just incredibly dense.
Very dense.
I was actually thinking about the stories you hear from veteran ER nurses who used to have to wrestle with those outdated 200-pound solid steel crash carts.
Oh, those are a nightmare.
Right. Like when a patient is coding 3 rooms down, a nurse throwing their entire body weight against a heavy steel cart just to get it moving down a crowded hallway that's a massive liability.
It is, and that is the fundamental physics problem engineers face here. You have these devices packed with heavy power supplies, lead shielding, motors.
Tons of heavy components.
Yeah, but a stationary piece of life-saving equipment is worthless in an emergency. In physics terms, it's basically an issue of inertia.
Because it's hard to get moving.
Exactly. A heavy steel part requires immense kinetic force just to start rolling. And then once it's actually moving, it requires a dangerous amount of force to stop or steer around a corner.
Which is terrifying in a crowded ER.
Right. So aluminium profiles drastically alter that equation.
Because you're dealing with an incredibly specific combination of mechanical properties. Aluminium is lightweight, obviously, but its load-bearing capacity is just completely disproportionate to its mass.
It punches way above its weight class.
Yeah. To help visualize this, I keep thinking about an ant's exoskeleton.
Oh, that's a good one.
Like, an ant is practically weightless. You can just blow it off a table with a breath. But the geometry of its exoskeleton allows it to carry, 50 times its own body weight?
At least, yeah.
These custom aluminium frames are doing something very similar, aren't they?
The ant analogy works beautifully because both rely on internal structural geometry rather than sheer density.
Right. It's not just a solid block of metal.
Exactly. By utilizing custom extrusion, engineers create these complex, hollow shapes with internal webbing that maximizes the strength while stripping away all the unnecessary mass.
So it's mostly air inside.
Essentially, yeah. So you have hospital furniture, transport trolleys, and automated mobility systems that can hold hundreds of pounds of sensitive gear.
But they weigh nothing themselves.
Right. A single technician can maneuver them through a narrow, crowded corridor with one hand.
And when you're, taking a corner at speed with a heavy, highly sensitive device, you really can't have the frame twisting or bending.
No, absolutely not. The rigidity of the aluminium profile absorbs that torsional stress. The frame maintains perfect stability.
which keeps everything inside safe.
Exactly. It ensures the heavy internal components aren't shifting or breaking during a high-speed transport.
So a lightweight, rigid cart is obviously a lifesaver during a rapid response. But, and this is where it gets crazy, the moment that equipment rolls into an ICU or an operating room, its physical weight suddenly stops being the main concern.
Right, the environment changes completely.
Now, it has to survive what is essentially a microscopic battlefield. We're talking about the relentless fight against healthcare-associated infections.
Modern healthcare relies on incredibly aggressive hygiene protocols. The chemical assault these machines face daily is just brutal.
I genuinely struggle to understand how the metal survives this,
It's counterintuitive for sure.
because hospitals are wiping down every single surface with industrial-grade bleach, quaternary ammonium compounds, and running extreme sterilization cycles, sometimes 10 times a day.
Oh, easily 10 times a day in an ICU.
If I leave a metal bike out in the rain, the moisture alone causes it to rust and degrade within weeks. How does a medical cart not just corrode into dust under constant chemical bombardment?
It all comes down to the fundamental chemical nature of aluminium. When aluminium is exposed to oxygen, an immediate, localized chemical reaction occurs.
Okay.
It forms a microscopic layer of aluminium oxide across its entire surface.
Like automatically.
Automatically and instantly. And this oxide layer is incredibly hard. But more importantly, it completely seals the raw metal underneath from further exposure to moisture, chemicals, or cleaning agents.
Wait, so it isn't like paint or a coating that can just be chipped away over time?
No, not at all.
The metal is actively generating its own protective shield from the air itself.
Exactly. And if we connect this to the bigger picture, the material's resistance to bleach is really only half the battle.
What's the other half?
The true war is fighting where bacteria actually live. When manufacturers like Eleanor Industries produce these profiles, they aren't just pouring metal into a mold.
Right.
They are engineering extruded shapes with exceptionally smooth, non-porous surfaces.
And by non-porous, we're talking about the topography of the metal under a microscope.
Precisely. Take the lower-grade metal or even certain medical-grade plastics. To the naked eye, they look perfectly smooth.
Sure.
But under an electron microscope, their surfaces look like the surface of the moon.
Wow. Just full of craters.
Riddled with them. Microscopic craters, pores, deep fissures, and to a Staphylococcus bacterium, those microvalleys are a perfect safe haven.
So a hospital worker can scrub that plastic surface with harsh chemicals.
But the wipe doesn't reach the bottom of the crater.
Exactly. The bacteria deep inside those microscopic pores can actually survive the wipe down.
That's the danger. But high-quality extruded aluminium denies bacteria that terrain. It is so remarkably smooth that the bacteria have literally nowhere to anchor, which drastically minimizes accumulation.
That is wild. The material itself is a direct, active tool for infection control.
It really is.
It's just sitting there in a sterile laboratory or an operating theater, taking the absolute worst chemical punishment without degrading, and literally giving pathogens nowhere to hide.
Which ensures the equipment is an active participant in the hygiene protocol, rather than a liability that slowly degrades over years of clinical use.
Okay, so the equipment is mechanically strong, it's highly mobile, and it is chemically fortified against bacteria.
Check, check, and check.
But that brings us to a much more frustrating problem for hospitals. Medical software and imaging sensors, they evolve at a breakneck pace.
Oh, constantly. Every few months there's a new breakthrough.
Right. So a $1 million diagnostic scanner built 4 years ago might suddenly be incompatible with a brand new, highly sensitive imaging sensor.
Which happens all the time.
Do hospitals really have to just throw away a perfectly good $1 million machine just because the physical rigid frame doesn't fit the new upgrade?
Historically, yes. And it was a catastrophic financial drain on healthcare systems.
I can't even imagine the waste.
The solution to that obsolescence, though, lies in how these modern aluminium profiles are actually made. The manufacturing process is called extrusion.
Extrusion, okay.
Yeah. Instead of casting a solid block of metal, immense hydraulic presses force a heated, solid billet of aluminium through a custom-engineered hardened steel die.
Like pushing Play-Doh through one of those shape molds.
Exactly like that, but with staggering kinetic and thermal forces. And what comes out the other side is a continuous profile with an incredibly complex, specific cross-section.
Okay, and here's where it gets really interesting. Because of that specific cross-section, I want you to envision these aluminum profiles as highly advanced adult Lego sets.
That's a great way to look at it.
They aren't just solid welded blocks of metal that you're stuck with forever.
Hmm.
The extrusion process allows manufacturers to build in continuous T-slots, interlocking tracks, and modular brackets right into the shape of the metal itself.
Built right in from the start.
Yeah. So if a hospital needs to upgrade an imaging machine with a slightly larger sensor, they don't scrap the whole machine.
They simply unbolt the specific section of the framework, slide in a new custom-designed aluminum extrusion that accommodates the larger sensor, and reassemble it.
Just clicking in a new Lego piece.
Exactly. By mixing standard profile sections with custom-engineered parts, hospitals achieve a fully scalable infrastructure. They adapt to evolving technological advancements without the devastating costs of complete system redesigns.
And there's a big but here, swapping out parts like Lego bricks only works if the new pieces fit perfectly.
Oh, absolutely.
The engineering tolerances have to be microscopic. When we look at the manufacturing output from places like Eleanor Industries, there is a really heavy reliance on CNC machining computer numerical control.
Right.
We were talking about precision measured in fractions of a millimeter.
That microscopic accuracy is absolutely non-negotiable in medical tech, and it mostly comes down to managing one specific physical threat vibration.
I assume you mean like the internal rattling of the machine's motors while it runs?
Yeah. Think about the stakes of an MRI or a CT scan. The patient is inside a machine that is taking incredibly detailed cross-sectional images of their internal organs to detect, say, microscopic tumors or hairline fractures.
The imaging is insanely precise.
Right. And the motors spinning those sensors generate significant kinetic energy. If the modular joints of the frame are even slightly loose, if the tolerances are off by half a millimeter, the structural frame will begin to resonate and vibrate.
Which brings up a crazy story. I recall this specific historical case study where a microscopic vibration actually led to a false positive on a tumor scan.
Oh, the stress fracture case, yeah.
Yeah. The frame holding the camera had a tiny stress fracture in a steel weld. And as the machine ran its 20-minute cycle, the camera vibrated just a fraction of a millimeter.
Almost invisible to the naked eye.
Exactly. But when the doctors looked at the scan, the slight blur caused by that tiny vibration looked exactly like a growing lesion.
That is terrifying.
The patient had to undergo a massive wave of anxiety, follow-up testing, biopsies, simply because the metal frame rattled.
And it is a perfect example of why the physical precision of CNC machined aluminium is tied directly to clinical outcomes.
It's not just an engineering flex.
Not at all. When those extruded modular parts lock together with microscopic precision, they effectively become a single, rigid, vibration-dampening unit.
They absorb the shock.
The aluminium absorbs the resonance of the motors. The camera stays perfectly still, the scan is crystal clear, and the doctor can make an accurate diagnosis. The stability of the frame ensures the diagnostic software can actually execute its purpose.
The tightness of a metal joint dictating the clarity of a tumor scan is just incredible to me.
It's all connected.
So the structure is precise and it's stable. But powering those spinning sensors and running that advanced software generates a massive hidden problem.
Heat.
Yes. I look at the computing power on modern diagnostic machines, and frankly, I don't understand how they don't just melt.
They get incredibly hot.
My laptop sounds like a jet engine just running a few heavy spreadsheets. How is an enclosed medical device preventing a total thermal meltdown?
You're dealing with processors executing trillions of calculations a second, generating immense amounts of thermal energy. If that heat is not aggressively managed, it will literally cook the sensitive electronic guts of the machine.
Just fry the circuits?
Yeah, degrading the sensors and ultimately destroying $1 million device.
And you can't exactly strap a massive, noisy cooling fan to the outside of a delicate medical instrument.
Especially not in a sterile environment, which means the aluminium frame has to take on a dual role. It's no longer just a structural support. It functions as a critical thermal manager.
Wait, the frame itself cools the machine?
Yes. Aluminium possesses excellent thermal conductivity at the molecular level. Its free electrons rapidly transfer kinetic energy away from a heat source.
That is so smart.
So manufacturers engineer specific extrusion profiles called heat sinks. They feature these deep fins and ridges to maximize the surface area.
Oh, I've seen those. They look like little metal accordions.
Exactly. And these profiles are mounted directly against the hottest electronic components. The metal physically draws the thermal load away from the processors and dissipates it harmlessly into the surrounding air.
It is literally pulling the heat out of the computer to keep it alive.
Pulling it right out.
And when you are preventing a $2 million machine from burning itself out prematurely, you are solving the overarching anxiety of every single hospital administrator, the budget.
The economics of healthcare infrastructure demand a high return on investment. It's a business, after all.
Right.
Because these custom aluminum profiles manage heat to protect internal components and resist chemical corrosion and allow for cheap modular upgrades, the maintenance costs just plummet.
Or lasts way longer.
A hospital is extending the life cycle of a massively expensive asset from, say, 7 years to 15 years simply through intelligent material engineering.
That's huge. But beyond the hospital's budget, there's the environmental reality to consider, too.
Oh, definitely.
We are so conditioned to associate heavy manufacturing and, metal casting with severe environmental damage. But when you examine the entire life cycle of this material, it becomes an exercise in deep sustainability.
Aluminium is uniquely eco-friendly because it is infinitely recyclable.
Infinitely.
Infinitely. When a piece of medical equipment finally reaches the end of its decades-long life cycle, the aluminum frame does not end up in a landfill.
That's a relief.
It is melted down and completely repurposed. And the secondary smelting process requires only about 5% of the energy originally used to extract the metal from bauxite ore.
5%. That's a massive energy saving.
It is. And crucially, the recycled aluminum profile retains every single mechanical property. It is just as rigid, lightweight, and corrosion-resistant as a brand new extrusion.
So it's a completely closed loop.
Exactly.
And it goes even further than the medical carts themselves, right? Because Eleanor Industries is simultaneously engineering solar panel aluminum extrusions.
They are, yeah.
They are actively helping these massive, energy-hungry healthcare facilities mount renewable energy grids right under their roofs.
It's brilliant.
So a hospital can use heavily recycled, eco-friendly metal to mount solar panels, generating green energy to power highly efficient diagnostic machines, which then use aluminum heat sinks to conserve energy.
It entirely shifts the paradigm of hospital infrastructure.
It really does.
The physical environment is no longer just a passive, decaying drain on resources. Through deliberate, precise material selection, the infrastructure actively drives the sustainability of the facility, both economically and environmentally.
So what does this all mean? We started today's journey by looking past the glowing screens and the flashing lights of a modern hospital to find the invisible skeleton hiding beneath.
And we found quite a lot.
We did. We found a deeply engineered material that carries massive weight while remaining light enough to sprint down an emergency room hallway.
Right.
We explored the microscopic chemistry of an oxide layer that fights off daily chemical assaults and denies dangerous bacteria a place to hide.
Which is saving lives every day.
Absolutely. We unpacked a precise modular Lego system that stops microscopic vibrations, ensuring that a life-changing medical scan is crystal clear.
Avoiding those terrible false positives.
Yeah. And we looked at a thermally conductive, infinitely recyclable metal that protects delicate computers while helping hospitals balance their budgets and embrace renewable energy.
It touches every aspect of the hospital.
It really does. So the next time you find yourself sitting on a hospital bed, or you see a medical trolley roll by, or you slide into a massive diagnostic scanner, take a second to look closely at the sleek metal frames holding it all together.
You might just appreciate them a bit more.
You definitely will. You are looking at the unsung engineering that is quietly making your healthcare safer, faster, and remarkably more efficient.
And this raises an important question, really.
Oh.
If this incredibly modular, perfectly adaptable, and infinitely recyclable aluminum Lego system can successfully future-proof our most complex life-or-death healthcare infrastructure, what other rigid, permanent structures in our cities and our daily lives are desperately overdue for this exact same modular revolution?